All right, so thank you very much, Jason. I also want to thank everybody for being here today. This is a wonderful turnout, a wonderful day. And I want to tell you a little bit about the research that we've been doing here at OU in my laboratory. I'm a professor in the School of Civil Engineering and Environmental Science. I am not an engineer, as Jason pointed out earlier, all the engineers. I'm in the school, but I'm an environmental scientist. And my laboratory is the Center for Restoration of Ecosystems and Watersheds, or CREW. So I want to tell you a little bit about what CREW does, and then hopefully finish up with some ideas on ways we might collaborate in the future. They say a picture's worth 1,000 words, so hopefully that picture in the background will tell you a little bit about the kind of work we do. That's one of our long-term research sites in northeastern Oklahoma, up in Ottawa County. So fundamentally, the big question is, how do we sustainably address these critical water quality and availability concerns? And as an environmental scientist in an engineering college, I like to look at that interaction. So scientists like to look at the processes, engineers like to design the solutions, but the really cool stuff is where those two things interact, where they come together. So for the work that we do in CREW, we like to look at the science side specifically from an ecological perspective. So biogeochemical cycling, microbial metabolism, things like diversity, richness, and abundance of species in the environment, biological uptake, and even some ecotoxicity work. On the other side are all those engineering design parameters, the hydrology, the hydraulics, the reduction oxidation reactions, diffusion, absorption, et cetera. So if that's where the cool stuff happens, I like to think that's where we fit in, because we're cool, and we fit into the cool part right there. So CREW does two major things. One, watershed biogeochemistry, which is really looking at drainage basin scale, materials and energy transport, how stuff moves through the environment. And so you see a lot of students in those photos, a lot of field work, water sample collection on lakes and ponds and streams, some work in collaboration with GRDA out on Grand Lake of the Cherokees. We're doing some cool small unmanned aerial system work now to develop water quality models looking at spectral reflectance and in situ water quality data. Our second push is the ecological engineering side, combining ecology and engineering design. So ecosystem conservation, restoration, creation, remediation. You see a lot of orange in those photographs. That's because a majority of our work is being done in mine drainage impacted watersheds. That's our contaminant of choice, or those ecotoxic metals, along with some traditional wetlands restoration work. That's kind of my first love, was in wetlands restoration. So some folks have seen this before. This is one of our long-term research sites. This is the Mayor Ranch Passive Treatment System at the Tar Creek Superfund site in near Commerce, Oklahoma, a 10-cell system funded by US EPA. These first 3 units promote oxidative processes. These units, the bioreactors, promote microbial reductive processes, and then we have some polishing units down here. But the whole idea is to build it and allow those natural processes, those natural mechanisms to take place. We don't engineer organisms, we build the ecosystem, and if we do it right, Mother Nature's gonna help us fix things. And sure enough, that system has been in place for 10 years. We'll have our birthday next week. Our 10-year birthday is November 21st. Oxidative processes on the top, you see the iron accumulation in those. We do use some solar-powered blowers to get air in the water, some directional baffle curtains. The vertical flow bioreactors include a network of perforated pipes, some gravel, and then a compost, that organic matter to promote those microbial processes. So I had to show some data because I'm a scientist, we like data. These are the contaminants of concern for this particular system: lead, zinc, cadmium, and iron. And you'll see inflow mass loadings on the left, outflow mass loadings on the right. That's 10 years worth of data. The N is about 85 for those. Significant removal of the contaminants of concern. The system is working. Some things that we didn't design for, arsenic, cobalt, nickel, we see significant removals. We also see removal of manganese in those systems. And just as importantly as where we do see removal, we don't see removal of things like base cations, calcium, magnesium, potassium, sodium. We're not seeing changes in those because we're not acting upon them biogeochemically or microbiologically, and we're not seeing big dilution issues influencing water quality or our mass loadings. So the chemistry is really interesting, but more importantly are things like this. So we have been sampling fish in the receiving streams before we began construction of these systems, and we're seeing significant recovery without actually doing stream recovery by just improving water quality. So we're applying this natural infrastructure to solve problems not just in mining areas, but also some work closer to home, the Trailwoods Low Impact Development System, places farther from home, a lot of work in South America. We work in Bolivia, and some ongoing work here in Lake Thunderbird, a little closer to home. But we build ecosystems, that's what we do. So A lot of things, the first few on that list are things that have been actively going on. We plan to continue with. A few at the bottom are things we're very interested in and just starting on. But thank you all for your time. Thank you.